Yeah, thanks so much for this really wonderful conference. I've enjoyed it a lot. And I'm very happy to tell you about some work that we've done looking at development. I'm thrilled to see that development has already been mentioned a couple times in this workshop, Steve yesterday. And then John showed this beautiful video that raises the question about the possibilities that a child's brain can develop into. And that's what I'm going to be discussing today. Some questions I want to ask is, how does brain structure change with age? What happens as a child goes into an adult? What are some things that we see accompanying these changes of maturity? Can we use network control theory to study some of these dynamics that emerge in brain structure? And to do this, we look at a large youth cohort and then some additional modeling that we've done. The first part of my question, the question that I asked was, how does brain structure change with age? And let me just unpack a little bit the kind of brain structure that I'll be looking at in my talk today. I'm going to be looking at white matter. And so one can think of the brain as being composed of gray matter and white matter. A lot of the talks yesterday focused on cell bodies, which compose gray matter on the outer surface of the brain. And one can think of the brain as being where the computational units are composed of this gray matter, and they're connected via the cell axons that go through the center of the brain. So we want to think about how these pathways of transmission that allow for the dynamical activity to be transferred from one part of the brain to the other, and to look at how this information transmission is facilitated by these pathways. So here, we use diffusion imaging to map out these white matter tracks, these large bundles of axons, so when they get reconstructed, like so, where we infer these white matter tracks from the movements of water molecules along these bundles of white matter. Then we can use these reconstructions to map out brain networks, where we're looking now at a large-scale network, so across the whole brain. So to do this, we divide the brain up into several hundred regions, where the brain regions are identified as nodes of this network that we construct. And traditionally, these brain regions were identified based on histology. And nowadays, with much better non-invasive techniques from MRI, we can then look at these brain regions non-invasively, which is really great because now we don't have to sacrifice monkeys, and in the past, certainly, this information would not have been possible outside of looking at human cadavers. And so the fact that now we can scan many subjects really is power and information that we can then use for our analysis. So to the second part of my question about how brain structure changes with age. And so to go into this, well, we see that kids already at a young ages, that their visual, motor, and auditory capacities are well developed, and they react very quickly to what is in front of them. However, one thing that presumably distinguishes an adult from a child is that an adult is able to pause and think, do I want to react to this immediately? What do I want to do? What is my response in front of this? And this is also an idea of cognitive control. One can think and plan and strategize. And do changes in brain structure reflect these capacities? And there are certainly morphological changes that we can see that accompanies the maturity of a child into an adult. And can we understand this more quantitatively? So cognitive control is really refers to these higher level processes where the brain controls everything, breathing, your heartbeat, but also thinking and processing. Just an example, during a lecture, you can pay attention, or you can listen to there might be other sounds going on, and you might be thinking about what is being said, or other thoughts, and so to decide what to focus on requires a choice, which in this case I hope is listening to this particular talk. But one can see that given several different conflicting stimuli, what do you choose to focus on? And traditionally, this has been understood in psychology via a centralized paradigm in which the front part of the brain, the prefrontal cortex, controls several other functions, in tandem with other regions that may be focused on different things, conflict monitoring, allocation of control, gating, and via various neuromodulators. But it's really this network that tends to be centralized, where the PFC controls other regions. And this is the predominance point of view that then we want to that our model will probably be most akin to today. So John already showed sort of a slide that kind of compares how one might think of sort of the brain as a network control as a system which employs network control, and how this might tell us something about certain biological processes of control that might be happening. So in this case, this is the sort of similar paradigm that we will be using, in which if one can think of cognitive control as a top-down process where a few regions, mostly in the front of the brain, influence many other regions, then this is a similar paradigm to network control, in which one can think of how the dynamical state of a network is being modulated via input to specific control points. And for example, in this schematic where there could be one main control point that controls the rest of the network. So then one can ask, how does specific network architecture support changes in states, which I think is a question that has come up in several times in this workshop. I mean, Fabio was also looking at similar questions, but in this case, what we want to ask is, looking at brain structure, how does the brain structure that we have and can measure facilitate changes in control? So then we will be using network control theory to study dynamics and what kind of dynamics could be supported by these white matter networks. And in here, again, it's great coming at the end of the workshop because all these ideas have already been mentioned, and John was telling us about network control. And increasingly, there has been a demand to understand the dynamics in real-world networks, and I think this has been a great push in recent years, because in real-world networks that are often large and floppy without a lot of discernible structure, how do we start to understand how the dynamics are actually being facilitated or changing in these networks? So this was a paper that studied several different real-world networks, and asking how in toy and other networks one might be able to then guide certain changes in state that one desires. And there has also been other work which is based on control energy considerations, and here I'm going to be using work by Fabio, and in which they have used control energy considerations to identify different possible strategies. So based on the kinds of control transitions that one might choose, then one can identify different driver nodes that might be more predisposed to drive to affect different kinds of changes in the network based on control energy. I will be showing equations for this in subsequent slides. So to get back to the precise system that we want to study now. So again, I had said that we do construct these brain networks, and what this gives us can then be described in adjacency matrices like so, where then our several hundred brain regions form the nodes of the network, and then the reconstructed white matter tracks from one region to another that describes the connectivity from one region to another, then forms the weights of this network. And so then this pattern of white matter tracks can then be represented as an undirected weighted adjacency matrix. This is the data that we have. We can then write down our dynamical model, and in this case, the brain is manifestly nonlinear. However, for short time scales, we will use some linear approximation based on these nonlinear models. And so in here, this is a linear time invariant model. The dynamical state at any given time, X is then mapped onto the next state by the weighted adjacency matrix that we derive from this diffusion imaging data. And then we have the control input. And here the state activity is probably most natural to think of it as bold activity, fMRI activity, which describes oxygen consumption in the brain. However, at the same time, this could also be used to describe electrical activity or something else if we're looking at different networks in the brain.
What should we think of when we look at U in this equation?
Say that again.
U is of what? So you say X will be activity at a given region in the brain. U.
So this is just the control input. This describes which regions we are actually injecting input into, and U here would be, I suppose more generally, what U would be sort of the time series of the control input. But in this case, we're just going to be thinking about a static case. So then UT is really just U, and probably describes the magnitude of how much energy are we putting into the system.
So I mean, U is an exogenous input, so we're thinking of this as sensory stimuli, things like these.
That's a great question, that definitely could be one way to interpret this. Since we do want to think about cognitive control here, the other way to think about it is that the brain is probably controlling itself at any given point. There's all kinds of things going on in the brain, electrical and chemical activity. So the brain is regulating itself in many ways. And so I think that's a great question, and perhaps I should have stepped back and said a little bit more about kind of the underlying framework that we're trying to talk about here. There's a lot of great work in trying to achieve very specific, let's say, synchrony or specific dynamics. However, here what we are trying to do also is now to use control theory as a way to understand mechanisms that may already be happening naturally in the brain, if possible. So the question is, given that the brain is obviously enacting many different kinds of control at any given moment, that I make a decision now about what to say or what to do, and we're all doing this all the time, how useful is control theory in helping us to understand some of these things that is already going on? And that's the question, overarching question that we're looking at. And this is efforts in that direction. So thank you. I should have probably stepped back and said a little bit more about what we're trying to do. Yeah. Are there any other questions, please? Yes.
So if the brain is controlling itself, and you put something that is X, X is the activity of the region, regions, and that you have actually some subset of activity.
So, yes. So the question is, since X is the activity and the brain is controlling itself, is U just X? So I think this could be the case for a much simpler system where there's just one kind of activity going on. But if we go back to the example I had given, let's say X is oxygen consumption in the brain. Then there's also, at the same time, in that particular region, there's also chemical input, there's also electrical input, there's many other things that is happening. This is clearly a very reduced model of what the brain is doing. But it's our attempt to understand some questions about development. So I will be using the control metrics that I had flashed earlier. And in this case, what we're using here is then we're going to be looking at the Brainian. And in here, just because we want to start to compare what one region is, sort of the relative control properties of one region with respect to another, we are also going to be looking at control region by region. So the B matrix is simply just reduces to the control input at one region, and then we look at then analyzing the Brainian, and especially its spectral properties can then tell us about the ease or difficulty of control. So in particular, we will be using average controllability, where since the eigenvalues are then an indication of the ease of control, we're going to use a trace of the inverse Brainian. And then for modal controllability, we will also use the eigenvalues, which is an indication of, the control of transient modes. And so then, as an extension of the PDH test, we will be using a scale measure of the eigenvalues for modal controllability. And for more details, I encourage you to either talk to Fabio or read his paper. And this other paper by Gu et al. Is then a discussion of the first application of these metrics into brain data. And so then, given that we do have our brain networks and that we do have these metrics, we can then look at what is happening across youth of different ages. And here we are using the Philadelphia Neurodevelopmental Cohort, which is a large cohort, 800 subjects from the ages of 8 to 22, and this data has passed rigorous quality assurance protocols. So now I'm going to start to show some results. And are there any questions so far? Please feel free to stop me because I've probably been speaking fairly fast. And so this is our brain data, and first of all, we wanted to start to look at what are just aggregate measures across the entire brain network before we start looking at regionally specific results. And so then we just simply average the average controllability and average the modal controllability across subjects, and that is the colored dots. Each dot represents the results for each subject. And then we also created two null models where we started from the same brain networks, and then we permuted we permuted the edge weights. But in one case, we permuted the edge weights such that the strength of each node, which is the sum of all the weights of each node, remains roughly the same. And in the other case, we permuted the weights in such a way that the number of connections that each node has remains the same. So these are fairly conservative permutation models. The same edge weight distribution permuted to keep certain properties the same. And we see here that in these null models, firstly, we see that brain networks show a higher controllability than the null models, and that these mean average and modal controllability metrics are positively correlated.
So in this case, what are the
So the A matrix is simply the brain network, this white matter network, the white matter connectivity of each subject. And so we're calculating this for each subject. And the B matrix is, as I was saying, we're looking at one region at a time. And so then we get a control value for each region. And that's what we are using, but I'm just averaging across the mean result from all the regions right now. And then we can look at how this changes across development. And here we see that the lighter colors are the older subjects, and the darker colors are the younger subjects. And we see that essentially, and this is more clearly shown here, that controllability increases with age. And then we are also using another measure of the dynamics that the brain networks can support. And here's synchronizability. Fabio had already discussed why this could be interesting in the brain. And here we are going to be using results that from Picaro and Carroll, in which they use the master stability function, where essentially they look at the Laplacian of a network, and when looking at and given the spectrum of the Laplacian, then one can see whether or not the eigenvalues of the Laplacian fall within the region of stability. In short, like if they are negative under the master stability function, then the system is stable under a state of synchrony, and otherwise, then the system will not be stable in synchrony. And it is more likely that the network will remain stable so long as these eigenvalues have a smaller spread, and hence we are going to use the spread of eigenvalues or the inverse spread of eigenvalues as an indicator of the synchronizability of this network. And what we see is that synchronizability decreases with age and is negatively correlated with controllability. And so together, this what we see about brain networks, both decreasing in synchronizability and increasing controllability, can be understood as that the brain is becoming more specialized with learning and development. Because, for example, one can think of synchronizability as being a homogeneity of length scales. And so the fact that subjects who are younger show this sort of more homogeneous networks in terms of its length scales, and this becomes more specialized, is a way to understand our results. We can then look at regional specialization, so then we can start to look at really region by region, what are the control values of each region, and we can also ask how do those regions change with age. And what this plot is showing is that the regions that are high in average controllability then are also the ones that are increasing the most with age. And so this is the idea of that the strong regions are getting stronger. And so this is, again, indication that the brain is becoming more specialized, or increasingly specialized with age. And we call them supercontrollers. We also see this similar trend for modal controllers, that strong regions get stronger. And I had begun my talk talking about cognition. What does this have to do with cognition? And so something that I haven't told you yet is that these subjects, this large cohort of subjects, besides having their brain scanned, they were also asked to do tests, cognitive tests, where they respond to lots of questions, and then they are scored based on their based on their speed and accuracy. And that is this y-axis. That cognitive performance is a similar measure to IQ. And one can ask, how do these developmental effects correlate or tell us anything about cognition? And in looking at this question, one can have a couple of hypotheses. One hypothesis could be, is it these like strong regions that are getting stronger, these supercontrollers, are they the ones that are more associated with high cognition? And we see, and here when we look at this, we actually see that the answer is no, that these strong regions are not the ones that are giving any differential kind of measure with cognitive performance. And instead, when we looked at the converse, when we looked at the regions that were not changing across age, and these are the stable controllers that are actually found in the subcortical regions, that then we found instead that the subcortical regions are negatively correlated with cognitive performance. And you know, one can think of the subcortical regions as being composed of, you know, the amygdala or regions that are more connected to emotional processing. And so this is consistent with some other things that we've seen in the literature. And this points to that the relative strength, it might be the relative strength of controllers in subcortical versus cortical regions that is critical for individual differences in cognitive function. Do you want me to end in 7 minutes? 10?
Yeah.
5. Okay. So in my last 7 minutes, I'm just going to be asking. This is interesting that the brain increases in controllability with age. Could this be some kind of mechanism? Could this be something that the brain is trying to optimize across development? And to look at this a little bit more, we used some modeling techniques of Pareto-optimization, where just to give an indication of the algorithm that we used. The question is simply that starting from a child's brain, can rewiring processes, a lot of which we know happen across development, there's a lot of plasticity, a lot of growth, a lot of pruning and rewiring. Can rewiring processes that increase controllability give us brain networks that look more like adult brains? And to look at this, we use Pareto-optimization, which I think you mentioned the word Pareto yesterday a little bit, and so basically it's given a couple of metrics, and they can be distributed, you know, in this space. The Pareto front is the front in which you know, in this case, I have networks. A network cannot increase in one metric without decreasing in the other metric. So it's the most efficient distribution of these metrics. And these networks that most efficiently satisfy these properties then lie on the Pareto front. And the algorithm that we use is that we start from an ensemble of real brain networks. So for each real brain network, then we create an identical ensemble of them. And in each of these 100 identical networks, there's an existing edge that's then swapped with an empty one. And then we look at this ensemble and how they lie on this space, and then we retain the networks that lie on the Pareto front and discard the ones that don't, and then we continually iterate this for thousands of steps. And so here these are the trajectories that we show, and the purple data is the empirical brain networks that we started out with. The yellow is when we were evolving to increase in controllability and decrease in synchronizability, which is what we see that happens across development. And we also did it in the opposite direction, just to contrast what would happen. So here we just see that, you know, they show similar functional forms, and which seems so it looks as if that increasing in control could be something of looks like what is also the empirical data is also showing. We can also look at the simulated trajectories and then ask what the differences are between children and adults. And we do see actually that the children's networks do show stronger, steeper slopes in modal controllability in particular, but not in average controllability, suggesting that children's brains have a greater capacity to optimize for more difficult transitions. And then we also compared with some other metrics, such as node strength, which has been shown to have a strong overlap with some of these metrics of average and modal controllability that we're using. It's much less constrained. We also looked at global efficiency or modularity or other metrics that one could associate with development as well, and they are less conclusive. And so I would like to summarize that Changes in white matter show an increase in controllability and a decrease in synchronizability that overall reflects increasing dynamics, increasing possible set of dynamics with age. The relative strength of controllers in subcortical versus cortical regions is critical for individual differences in cognitive function, and we use Pareto-optimization to try and model some of these trends that we see. Lots of other cool questions. In particular, I am very interested in this question about how can we understand better what kinds of topological structures underlie these changes in increasing dynamics that we see. Other questions that I would love to discuss with anyone who's interested. I would like to thank my group and my collaborators. In particular, this is my theory group, my mentor, Danny Bassett, and these are our experimental collaborators that helped us to collect the data and look at the NL funding agencies. And yeah, thank you for your attention.
So now we have our first both scientific and mathematical proof that old people are set in their ways. Now, this wasn't a prelude to your question.
That's fine, I can say it. Evelyn, so, the video that I opened with pointed out that the connection of the infant is going to decrease in connectivity by roughly an order of magnitude by maybe age 2.
Mm-hmm.
So is that what you think might be causing this lack of synchronizability?
So that's a great question, and it is true that the brain networks of adults are significantly sparser than the networks of children, and that's something we try to control for, just the density, and we try to do that by actually the white matter tracking algorithms that we use. We try to sort of keep the number of streamlines consistent. That effect is still there. We try to control for it, and hopefully we're trying to understand its topology we try to zoom in on hopefully differences in topology that are causing these differences. But of course so I would say that our results point to differences in topology, hopefully because of these reasons. But then there are in real life development, there's other things happening as well that probably contribute in different ways.
The way you are getting the image is symmetric.
It is symmetric. This is a limit of the data that we have, that the diffusion is not directional. So.
But in a brain, probably means that range.
So in the brain, things.
How important is that?
How important is that? So that is true. At the same time, most connections are bidirectional. And there's only a small fraction of connections that are just purely unidirectional. But at the same, and so there will definitely be a difference with real brain networks, and but at the same time, just because a lot of connections are bidirectional, hopefully there won't be too much difference.
Given that the myelination process itself is developmental, that is the amount of myelin that you can measure along the axon changes with development. Do you believe that that's an accurate way to assess the activity between children who might have a low proportion of myelinated axons and adults with a much higher proportion of axons that you can actually measure with DPI?
What is your question? Are you asking whether white matter can be more easily detected in adults or children?
I was asking whether it is appropriate to compare white matter as a measure of connectivity in children with a low myelination rate as opposed to adults, even if the connections are greater in children.
So this diffusion is going to just pick out the way that water molecules are being pushed in a certain direction. Certainly myelin is going to help with that, but even even with less myelin, it is thought that the connectivity will still constrain the water molecules to move in that direction. So there may be differences, but I think that white matter imaging is still a valid way to infer connectivity in children as well as in adults.
Okay, let's thank Evelyn again.